Hello students, in this video we'll discuss the sample mean random variable. If we're given a population, and we can just geometrically visualize our population of the entire world. Here's our population. And the population size is n capital, maybe 7 billion people, 8 billion people. And then we have a sample, a very small sample of our population. Here's our sample of our population. And the sample size is n. And so the relationship between our sample and the population, of course, is that n is just much, much less than n, right? We might be able to sample 10,000 people, sort of reasonably, right? Or 100 people if we're doing it on a small scale. We can conduct a survey at our university or at our high school and get about maybe 50 to 60 to 70 maybe 100, 200 samples. So sample sizes are relatively small relative to what? If I said, do a survey at your high school or your college or your elementary school, whatever it happens to be, and I say, well, relative to the entire population of all high school students or all college students, that's a much larger population. You don't have access to that information. So we have a sample n, and now what we want to do is we want to consider random variables. Or we can think of these as like random samples. x1, xn, right? So we can think of these random samples as the amount of something that a person in that population, in that sample population does. So x1, for example, might be the number of minutes that a person spends reading per day. And that will change from day to day. Maybe one day it's 30 minutes, the next day it's 40 minutes, the next day it's 0, the next day it's 2 hours, the next day it's 0, the next day it's 3 hours. That will change. And let's assume that they have some sort of underlying distribution, that the distribution is the same. And that these variables and the statistical assumptions we make are independent. They're independent and have the same distribution. They have the same distribution as the population, as the whole population. Okay? And let's suppose that this population distribution is x. And furthermore, let's suppose that this population x has the following properties, with the expected value of x being some population parameter mu. So this is the population mean, which we have no access to get. I can't sample every single college student in the country and ask them how much they read per day. It's infeasible to do that. So that's the population mean. We don't know that. It's unknown. We have to estimate this. And then we can say that the variance of x is sigma squared. That's the population variance. We don't know that. We don't know how much it varies from person to person. Population variance. Okay? So those are two things that we know from the population. I don't know what mu or sigma squared is. So I'm going to need to estimate them from my sample. And so what's one thing we could do? You could say, well, I'd like to estimate the mean, for example. So my estimate for the mean, there's lots of ways to estimate it. Estimate for the mean. My estimate for mu is going to be this statistic, x bar, which is x1 plus x2 plus xn divided by n. So in other words, I just do the what? This is just the average of those random variables. This is just the average, the statistical average, okay? And so now, what do I know about this? This estimate is actually what's known as an unbiased estimate. Let's compute the expected value of x bar for any n. So the expected value of x bar is going to be the expected value of x1 plus xn over n. You can pull constants like n out of the expected value. So I have 1 over n, the expected value of x1 all the way down to xn. Add it up. And now this is going to be what? This is going to be 1 over n times the expected value of x1 plus the expected value of xn. Now they all are what? All of these samples are independent and they have the same distribution. So all of those expected values are what? These are all going to be mu's. So what do I have here? I have n mu's inside my bracket. So I have n mu times 1 over n. So this expected value over here is just what? It's just mu. So the expected value of x bar is the population parameter mu. Great. So it's an unbiased estimate for the population parameter. Now, of course, what happens as the sample size, you might say, well, this is true when x is equal to just 1. I just draw one sample, and that's my best guess. If I had to give you the best guess for the mean, I would just pick a person at random and say, tell me how much you read today. And that would give me at least sort of that would give me some estimate. When you only have one person to draw, that's the best you can hope to do. If you have two people, it's the best you can hope to do. With two people, you can say, what did you read? What did you read? I'll average those and get something that's close to the what? The average or the mean value of times that someone spent reading. Now, let's compute the variance. So what's the variance of this estimator? How much does it change based on the sample? Well, this is the variance of x1 plus xn over n. Now with variance, you can pull out constants, but you have to square them because it's a quadratic operator. So when I take this 1 over n inside variance, I have to pull out with a square. So this is going to be a 1 over n squared, then the variance of x1 plus all the way up to xn. Now the variance of a sum is the sum of the variance provided that the observations are what? The random variables are independent. So this is going to be, by the same reasoning, it's going to be 1 over n squared, and I'm going to have n copies of what? The variance of any one of them is sigma squared. So the variance of this x bar is equal to, one of the n's is going to cancel out, and you're just going to have 1 over n sigma squared. So this is going to be sigma squared over n. Now, something very nice happens over here. This says that the more samples you add, as n gets larger and 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 larger, what's happening to the variance of this estimator? The variance of this estimator is getting really, 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 really small because you have sigma squared over n. As n gets really large, like a million or a billion or a trillion, then you have a huge number in the denominator, which makes the whole thing smaller. So the more terms you add to this sample population, the smaller the variance of the estimator becomes. Thank you very much.